Let's now consider the power dissipated by an oscillator, so that is the power used to drive it in steady state. Power is given by force times velocity, so we need an expression for the force applied to the oscillator. That's just the driving force. So from our equation of motion, we have this driving force here, so we take the real part of this, and that's our driving force. The velocity is something we've found in previous videos, so the velocity is given by this in terms of the mechanical impedance, and we take the real part of that, multiply it together, and we get an expression for the instantaneous power as a function of cosine omega t and cos omega t plus theta. So this is the instantaneous power at any given time t. What we're more interested in, however, is the average power. So we integrate over one cycle, that is over one period of these oscillations, and find the average power over one cycle. So as we integrate over one period, capital T, given by this, integrate from 0 to t, and here's the argument of the integral here, the power. Substitute in our expression up here, and we get an integral of these cosine functions, expand them a little, and we find one part here will integrate to 0 because the integral over one period of cos omega t times sine omega t will be 0. The integral of cos squared omega t, however, is not 0, it has a positive area. So in fact, 1 on t integral from 0 to t cos squared omega t is a half, so we can use that to replace the integral of cos squared omega t, and we get a factor of 2 down the bottom here and a cosine theta. Now I can simplify a little further by getting rid of the cosine theta, because theta is the argument of this complex number here, mechanical impedance, or the negative argument, but we take the cosine. We don't care whether it's positive or negative. So we just want to find the argument of this complex number. So it's the real part divided by the absolute value. So substitute in that here, and we find we can get rid of this cosine theta. To give this expression here, we get an extra factor of the absolute value of the impedance down here, and an m gamma up the top. Now we can also use, we can get rid of the mechanical impedance altogether as well by recognizing that this term here looks something like the amplitude of the oscillation. So the amplitude of the oscillation was given by this in terms of the force and the driving frequency and the resonant frequency, and it can be expressed in terms of the impedance like this. So in fact, we can find the total average power is given by m gamma a squared omega squared on 2. This is for mechanical systems. If we want to have an electrical system, then we can use the substitutions that we used previously, and then find the power dissipated by an electrical circuit is given by this, with the angle of the impedance, or getting rid of the angle of the impedance given by this. What about the maximum power? Well, the maximum power will occur when cos theta is equal to 1. So we want to have theta equal to 0. So that occurs on resonance. So we have maximum dissipated power on resonance. That's the point where you're injecting the maximum power into the oscillator, and the oscillator itself will be doing the maximum amount of work. Off resonance, so far off resonance, the power dissipated will head towards 0 as this angle goes to plus or minus pi on 2. It's also worth just remembering here what power we're talking about. So the force, this driving force in this equation, is doing work on the oscillator, and the work is being dissipated as heat by the damping in the oscillator. So when we talk about the power, we're talking about the power deposited by the driving force and the power dissipated by the heat due to the damping. Now we're going to ask the question, how resonant is my resonance? And this is an introduction to the concept of a Q factor. Now the Q factor measures the sharpness of resonance of the system. So let's think about a curve here where what we're doing is driving a resonator, and we're increasing the driving frequency until we hit resonance here. This is the resonant frequency. We go past resonance and the response drops. And what I've plotted here is the power dissipated by the resonator. Now there's a point here when we go down the curve where the power dissipated is half the maximum. And so we measure the frequency difference between this point and this point, where we both have half the maximum dissipated power, and this is called the full width at half maximum, and we call that frequency difference delta omega, the difference between omega 1 and omega 2. The Q factor is defined as the resonant frequency, omega naught, divided by delta omega. So it's this equation here. How do we find Q? In other words, how do we find this frequency at half maximum and this frequency at half maximum? Well, here's our equation for the dissipated power. I've re-expressed it slightly differently here, but it's the same equation. So we need to find where this power drops by a factor of 2. So Pmax occurs when omega is equal to omega naught. But when the energy of the system is halved, we must have these two terms equal to each other. So it's this term here must be equal to this term here, and that is when the power dissipated is exactly a half of the maximum, because at maximum this term here disappears completely and we just have this numerator here divided by gamma squared, and so when this part here equals gamma squared, then we've reduced the power dissipated by a factor of 2. So to solve this equation, in fact it's just a quadratic equation, and we find values for omega 1 and omega 2. So we solve it and we find that the difference between omega 1 and omega 2 in fact is given by gamma, which means that the quality factor, Q, is omega naught divided by the damping gamma. The quality factor, omega naught on gamma, is also the energy stored in the oscillator divided by the average energy lost per radian of motion, and it's also the number of cycles an undriven oscillator goes through before its amplitude decays by a factor of e to the negative pi. So these two things are equal also to the Q factor, and that's something that you can prove. So let's get some intuition about how quality factors work using audio signals. So here I've got Mathematica playing a sinusoidal tone, so a single frequency tone, with a decay time of 1 second and a frequency of 100 Hz, and it sounds like this. Kind of like a plucked guitar string. It decays about the same time as a guitar, and the quality factor is about 300. Now if I double the frequency here, it has the effect of doubling the quality factor. Although the decay envelope is the same, the number of cycles within the decay envelope has now increased by a factor of 2, so double the quality factor. Sounds like that. For a fast decay, so 0.1 of a second, it's a quality factor of about 60. Very long decay, then we can barely hear the audio signal die out. The quality factor in this case is around 6,000. And finally, here's a summary of all the different relations that we've used throughout this section on damped driven harmonic oscillation. So relationships between mechanical and electrical oscillators, the damped natural frequency and the undamped natural frequency, and all the different values of the angle of impedance and everything else.